Девичья фамилия
Yes,
Дач.
thanks.
Yes. Ну, so,
That's okay.
такой немножко солдатский юмор. Ну, что поделаешь. Вот. Так
Yeah.
что слушаем вас там всем вниманием. Да, и чтобы не забыть, в следующий раз у нас будет Тимур Ройберг. И по причинам, там, связанным со временем, он начнет в 5:30, а не в 6, как обычно. Просьба это иметь в виду. Ну, а сейчас с удовольствием предоставляю слово Анару. Слушаем.
Yeah, thanks. Okay, yes. Hi, everyone. Hope is all fine with my screen and hearings. We have a power cut problem in my country, so it's quite possible you may have a power cut problem. But please wait me about a minute until we have a generator is going to be back.
Yes.
Okay. Yeah, so what is mean a function system? So first of all, a concrete function system is just a unital self-adjoint subspace of a unital commutative sister algebra. I mean, it's just unital self-adjoint subspace of the sister algebra for all continuous functions on the compact set, Hausdorff compact space. Okay, so but the abstract one is defined something else, is an ordered star vector space with an Archimedean order unit. Well, I will explain what is that a bit later. So every function space, function system, turns out to be a unital star normed space equipped with a order norm. Well, I will explain what does order norm mean. So overall, all possible order norms are equivalent. They are running between min and max order norms. Yeah, that's a starting point is due to Paulson and Tom Ford from 2009. Well, in the theory of Banach lattices, the function systems, they are referred as the ordered vector space with their strong order units. Well, the famous result, the K-Descent representation theorem, state that every abstract function system can be realized as a concrete one on its state space, equipped with the weak star topology. That is a famous realization theorem due to K-Descent. Again, you will see below about it. But just brief introduction. Well, but in the quantum function analysis, for example, we can refer the book Alexander Yakovlevich of 2009. Well, we know what does operator systems mean, right? So the function systems, actually, they are sort of commutative operator systems, or operator systems equipped with various unital quantum cones. They are sort of quantizations of the underlying function system. Well, again, what is operator system? Probably you know, it's a unital self-adjoint subspace of the algebra of all bounded linear operators, B of H. So I need to put something like that, maybe like, okay, yeah, now it works. So the quantization principle of a unital cone in a unital star vector space, they were mainly developed by Paulson, Todorov, Tom Ford. They have he's the students of Paulson. They have a bunch of works starting from 2011 in this direction. So they are sort of categorical background of the abstract operator systems to develop the constructions, various sort of constructions parallel to operator spaces. Well, you know, after the classical result by Choi and Frost on abstract characterization of the operator systems.
Yeah.
Yes. So next, the classification problem of operator systems among the operator space structures on a unital star vector space that was investigated in my work about in 2019. So what's happening here? If you have a star vector space, it turned out the operator system structures and operator space structures, they are in a sort of they're almost one-to-one. I mean, we can always find some operator system that responding to a certain operator space structure. Okay, let me rub out this one. Okay. Yeah, but practically it's not clear how to detect unital cone or related to a certain operator space structure. For example, we have a problem with a projective tensor product. Even just one sum of operator systems, they do not exist in this proper sense. Well, let me explain what's going on here. For example, let's try to define one sum of operator systems. And trivial operator space, C plus C, we know what is that, right? So it has an operator dual, V star. Well, V possesses the natural involution, right? Z star. And we know that this involution actually, I mean, the norm is a star norm here, just preserve the star. Well, concerning unit, we have a problem. So, for example, we can choose this sort of unit here, right? The unit vector, say, and then try to generate state space. For example, we can look at all functionals, Hermitian functionals. They are unital functionals, right? With respect to that E. So if you calculate this one with respect to norm here, I mean, with respect to this duality, this one just means the sum should be 2, right? And so what does state mean, actually? State means sort of unital functional and should be norm at most 1. So if you look at this intersection is just degenerate to a single point, 1, 1, nothing else there. So having this sort of state, you will get nothing almost. So actually, there is no standard cone here. So there is no operator system structure here at all. Look, this is a typical example. So how we can define order here in C plus C? Well, what is that? What should be a reasonable order here? I mean, in operator sense. Okay. So overall, the construction of projective objects within the category of operator systems, it's causes a serious challenge. Even for the quotient, is not so easy to get the structure of cones. Anyway, so that's the main moment. So we wish to understand what does projective positivity mean in general. So we can attack the problem even on the level of commutative level. I mean, even for function system, that's not clear. What is that? Yeah, let me start. Elementary introduction. So probably you know what is that. For example, what does operator system mean? We know what is an operator system. Operator system, it's a unital self-adjoint subspace of B of H. Look, that means unit inside of V, and it's self-adjoint. For example, unital sister algebra is an example of an operator system. Yeah, in operator system, we can talk about Hermitian elements, right? Hermitian elements self-adjoint, and we can talk about the cone of positive elements. It's a topologically closed cone, and also algebraically. So it's separated. So it's a very nice cone. V plus intersection with minus V plus is 0. Well, what we can do with this cone, well, you know what? So what does mean unital cone means? V plus minus E absorbs all Hermitian elements. So that means every Hermitian element is actually belongs to this one, right? So if you divide by norm, it's going to be a unit operator, so adding up 1. So in the amount of spectrum, you can easily see that it's going to be positive. Well, and automatically every X is going to be written like different of positive elements. Yeah, we know this structure, for example, for sister algebra, but this is much easier here for operator systems. Every X can be written like a difference of positive elements. Well, using the positive elements, you can also restore all the all the operator system, right? That's also clear. Real part, imaginary part, and so on. Well, concerning functionals, right? For every linear functional, we can define its star. That's a routine way, right? If mu star, mu is called a Hermitian functional. And the vector space of all Hermitian functional is denoted by V star H. So what does Hermitian mean? So you can easily prove that mu is Hermitian if and only if mu is sending Hermitian to Hermitian, right? Sending all Hermitians to real. That's easy just. So even you can calculate the norm just using the ball of the Hermitian part. Right. Well, it's also well known what does positive functional mean, right? Mu is said to be a positive, is sending positive to positive. That means positive. Well, as you know, in this case, mu is automatically bounded, and norm will be just the value at E. And the positive functionals, they're again generating a cone. It's denoted by V star plus. It's a cone of all positive functionals. Okay, what does state mean? You know, phi is a positive functional, which is also unital. Right? Phi at E equals 1. That's so-called the state space of the cone. For example, in the case of the unital sister algebra of continuous functions, right, on the compact topological space, T, this is just means the set of all convex set of all probability measures, right? That's exactly probability measures on this topological space. Well, again, now let's look at the general case. So we can look at this real hyperplane, just all unital functionals. That's our notation, VHE star. So all unital Hermitian functions. So in this sense, again, state means functional whose norm is at most 1, and unital, right? That exactly means intersection of the ball of the dual space with this real hyperplane, right? That exactly means state. You have a real hyperplane and intersecting with the ball. So in particular, it's a weak star compact set, right? So why we need this state? Well, you can easily guess. So, for example, if you get a unit vector, you can generate this sort of positive functionals, right? And the actual states. So in particular, using these functionals, you can easily prove this one, this sort of bipolar theorem for states. I mean, X is positive if and only if its action over states will be positive. So we used to say like the positivity in operator system is just state positivity, right? Well, using state, we can also define a new norm, right? It's a new norm, look like that. Just this notation means the soup of all action states to fixed X. So it's a unital star norm, which is actually equivalent to the original norm. For Hermitian elements, they are the same. Well, this is an order norm. Look, that's a definition of order norm. For all Hermitian elements, there's going to be infinitum over all R, which is X is running with minus R and R. Right? Well, if your functional is Hermitian, then you can calculate its norm in terms of this norm, E norm, unital norm. Okay, finally, that representation, the Cartesian representation on the state. So you're getting X, action over states, like using the duality. So look, this one provides you representation. This is a unital, right? Unit element turns out to be a unit function, right? Constant function. So if x is positive, the image is again positive function. Well, if you change also the norm, you can have all the isomorphism and isometric mapping onto its range. So that's sort of commutative representation theorem, right? Commutative representation theorem for operator systems. It's quite natural. So this one exactly means order isomorphism. So positivity here exactly means functional positivity, right? Well, if the original norm equals to that norm, E norm, then we can identify V exactly with the subspace, unital star subspace, right? We used to say it's a concrete function system. So our V is a concrete function system up to an isometric. So we almost prove the following, like V operator system is a function system if and only if we have the equality of norms, right? So it's sort of commutative structure, a commutative function system. Okay, now look what we are doing here. We're going to do something else. Now let's take operator system again with a unit. This is our standard cone, right? This is our state space. Well, I told you what the state means, right? So real hyperplane intersection with the unit ball. Now I'm increasing a ball a bit, epsilon here. Look, epsilon more than or equal 1 in the dual space. This also makes sense, right? So it's a common set. So let's use this notation, S epsilon. Now, an element, Hermitian element, is said to be epsilon positive if this inequality holds in V Hermitian part. Right? If this one happens, we say that V is epsilon positive. Certainly, epsilon positive is automatically positive. Right? This number is positive, norm E. So V epsilon is inside of V plus. V1 epsilon is the same V epsilon. Well, this is also nice. Cone is a separated closed cone. Epsilon positive elements. Well, we can describe its state space of the cone. Look, the state space of the cone. Again, state means that they should be positive, epsilon positive, and unital, right? So it turns out the state space of the cone is actually, that's our exactly S epsilon. And this can be driven from the original state space. Look like that. It's a sort of convex, but not convex combination. We have minus here, so we are a bit enlarging it. So we are enlarging this SV epsilon in this way. Look, S is running between 0, epsilon minus 1/2. So this is a sort of technical lemma, tells you what's happening with the state space. Well, in the same way, we can define epsilon norm, like above this, I might have epsilon norm using the state space. Well, actually, this epsilon norm is equivalent to original E norm for every epsilon. And for epsilon 1 is just the same norm. So we are not spoiling this, the general picture here, general photo is almost the same. So but we got something equivalent. Well, let's see. What does epsilon positivity mean, for example, for functions, the standard functions? Let's look at the case of the continuous functions on the Hausdorff-Compact topological space. Again, Vf is a real-valued function, is said to be epsilon positive if this one holds for all t. Well, it's a bit weird stuff. We don't know what is that. Now let's try to clarify what's the meaning of this one. Well, you know from mathematical analysis course, so oscillation of a function, right? Measuring the highest amplitude on a certain set, E. Okay, so let's introduce one more definition, and eventually you'll see they are the same, actually. So a function, positive function, is said to have epsilon oscillation if either it's zero or its oscillation of its ln has an upper bound like that. So as you can see here, f should be strictly positive to take it ln. Otherwise, everything will collapse, right? For epsilon equals 1, there's going to be sort of infinity, and everything is admissible, so you're getting just every positive function has an epsilon oscillation here. Yeah, so if epsilon equals 1, every function has epsilon oscillation. Well, this elementary, for example, if you take 0, 1, epsilon is 2, 3 power t, it has 2 oscillation. But if you get more powers, 3 power 2, it has no 2 oscillation. So oscillation is sort of some boundary for amplitude. It should be in a certain range. Okay, now let's prove some critical lemma. Look what's happening with our positivity. So V is an operator system, and we have its Cartesian representation. Then the equality holds. So epsilon positivity in here for operating system, it exactly means epsilon positivity for space of all continuous functions. And for every Hermitian element, the following are equivalent. V is epsilon positive. Phi V as a continuous function on the state space has epsilon oscillation. And we have the bipolar property. The epsilon positivity means state positivity, right? You can get this positivity through the state space. Look, all these three conditions are equivalent. Well, again, in the case of space of all continuous functions, well, let's just test this lemma in this case. What is that? So, you know, this probability space is our state. The boundary is our original topological space. Star representation is reduced to this one, right? It's a sort of extension of every continuous function to probability measures. Look like that. For example, if there's a delta function, it's just original value, f at t. This is our Cartesian representation. So my claim is that, in this case, unital cone of epsilon positive elements, they're exactly functions with epsilon oscillations, precisely. Well, you can see here the sketch of proof, what's happening here, the technical backup of this theory. So one side, if function is epsilon positive, then phi of f has epsilon oscillation. This is due to lemma. Well, if phi of f has an epsilon oscillation on a bigger set, it has also epsilon oscillation on the smaller set, right? T. Well, conversely, it's interesting. So if function f has epsilon oscillation, you remember the ln condition. So you can take exponents, you can simplify in this shape or in this shape. That's true for delta functions here. Well, again, we can plug in instead of here linear convex combinations. Nothing will change. So if you get the convex combination, get the weak star closure, then still you have this sort of inequalities, right? So leaving all this to the left, you will see that it's all about state space. So you have a state positivity. Again, by lemma, this is equivalent to the epsilon positivity. Look, that sort of idea what we are doing inside. So what kind of stuff is running in. Okay, now let's switch to abstract case. Forget about operator systems, right, that we wish to understand in the general case. So now V just a complex vector space with an involution. So suppose we have a norm, right? Norm is said to be a star norm, means the ball should be Hermitian, like that. So that's equivalent to say that V star norm equals to V. Again, we can talk about Hermitian elements. Again, we can talk about the star involution on the dual space, like the same relation for phi star. Again, we have this property. So overall, this couple VV star turns out to be dual star pair, a dual star couple. So involution is weakly continuous, right? Again, we can talk about the space of all Hermitian, bond Hermitian functionals, and so on. This is quite a general case. Now, what is unit? What does unit mean here? So fix a non-zero Hermitian element, right? That's candidate for our unit. Again, we can generate real hyperplane of unital Hermitian functions. Again, we can take this intersection with the ball. That's all sort of state space, like it's a convex set. So that's important for us. What does unit mean? Unit means E is a unit if state is not empty. This set should not be empty. That's quite possible this can be empty set. Well, if it's not empty, you can choose Y and do elementary estimation. Look, norm Y is less than or equal 1. And you can see that norm of E should be more than or equal 1. Right? This is a definition of a unit. In our framework, unit means this one. For example, every Hermitian unit vector of a star normal space is a unit automatically. For example, if you get a unit vector, we can choose Y by Hahn-Banach extension property from the ball. And then you can take its real part, right? Because it makes sense, it's a star space. So this one is going to be Hermitian. So if you apply to E, result again will be 1. So that's real part will be exactly our state, right? So since E is a unit vector, we are getting that state lies in the unit sphere, in the dual space, right? So anyway, the general definition, a star normed vector space with a fixed unit is called a unital star normed space. This is a definition of a unital star normed space. Now, let's look at the unit ball. So look, there's a crucial moment here in our discussion when ball will be an absolute polar of the state space. That's exactly the same happened in for the function system or operator systems, right? Yeah, if this one happens, we say the ball is unital. So unital star normed space with a unital ball, that's called abstract function system or commutative operator system with a state space S. Look, that's quite a general and quite a simple stuff. So what we need from this V and state space, right? It should generate our norm, and also it defines the unit element. Yeah, we say that V is again function system, just briefly. So look, that's a moment. That's quite straightforward how to prove that if V is a function system, then you can define the cone and norm. C will be separated closed unital cone. whose state space will be S, norm will be that unit norm or unital norm. And E turns out to be a unit vector. Look, that's ideal case. So if ball is unital, and we can also define Cartesian representation again in the same way, right, on the state space. So it turns out to be order and isometric isomorphism. So this couple is a concrete function system on the state space. Right? Okay. Anyway, so if ball is unital, so situation is very similar, right? Like the previous one in operating systems. Everything is fine. Okay, now we have a challenge, but how to be if ball is not unital? That's exactly the case happening in the examples. So you will see below. Again, we are doing the same idea. We are generating epsilon, right? So a bit enlarging state space. So in the non-unital case of a ball, we try to find epsilon so that its absolute polar will be equivalent to ball. Not equal, but equivalent. Yeah, that means equivalence of balls, right? We know what is that. It's also ball, so the equivalent means this one. Well, if ball is equivalent to S1, it's like a previous case, unital case. Then norm will be equivalent to norm of E. Again, it's a concrete function system on the state space like the previous case. For example, every operator system, if you ignore its quantizations, whatever non-commutative structure, it's a function system up to an equivalent norm. Right? Okay, so now suppose V is a unital star vector space. This is our enlargement, epsilon, and this is our cone. So let's formulate the main result of our talk. So what's happening here? Suppose unital star normal space. So we have a unit, and look, this is our state space. So we have seen that S1 may not be defined, may define nothing just. But if you take epsilon strictly more than 1 over norm of E, right, then ball will be equivalent for every epsilon. And you can define also epsilon norm is going to be equivalent to original norm. C epsilon is a nice cone, right? So state space will be S epsilon, and this couple turns out to be a concrete function system on this S epsilon space. Look, so this one telling you, so if you enlarge a bit, that will be enough to get the similar picture here. Well, let's explain our example, what's happening here. How does it work in the reality? For example, let's look at the case LP2 spaces, two-dimensional LP spaces. And let's again explain the case of L infinity first. We know it's an operator system. It's a unit. But anyway, let's review what's happening in this case. If you take V star, it's going to be one sum. Ball, well, ball will be sort of this one, right? Like sort of rhombus. So if you take the star of the functional, this star is reduced to normal star. This is also clear. So you can try to generate the same real hyperplane. Real hyperplane will be a line connecting 1, 0, 0, 1. Okay. And now let's calculate state space. So real hyperplane intersection with the ball. If you get this intersection, that's easy. Like you're going to have exactly line the positive segment, right? positive side of this line, connecting 0, 1, and 1, 0. So in this case, state is just a line segment connecting 0, 1, and 1, 0 in R2. Yes, you can calculate the norm again. Norm is reduced to infinite norm, as it used to be, right? So ball is unital, and V is a function system. This is a classic. This is okay. This is quite normal. So positivity means state positivity, which is possible if and only if. So the coordinates should be positive. So that means our cone is just standard cone, first quadrant of the plane. So look, the theory works like straightforward. No problem here for infinity. But we have a problem whenever it's not operator system. Now look at this one. Now let's say P is less than infinity. Right? This is our target. C plus C, P sum. Well, for P sum, we have this unit. Well, let's take the unit because we said that every Hermitian unit vector is a unit. Look, this is a unit. Again, for V from the sum, Z star, norm of Z star equals to norm of Z. That's again quite simple. So ball is Hermitian. Okay, let's calculate state space for this case. So VEP is a unital star normed space. Its dual will be Q sum, right? For conjugate couple P and Q. So real hyperplane looks like that. It's again line. Well, if you look at intersection, that's going to be this one. So we have our Q ball intersection with this line. But you can easily calculate using the derivatives like standard calculus. You can see that it's actually this line will be exactly a tangent line to the ball. So intersection again, just single point. Look, that's a moment. So state provides nothing here apart from just single point. So having a state as a single point, you have nothing, right? So the cone is not separated and you have no norm at all, right? Okay, look, that's a moment now, but we have a construction with epsilon. Yeah, so look, S1 is not separated, ball is not unital. But if you use the epsilon more than 1, it provides a unital ball by our theory. Actually, you can catch up original cone for this epsilon, 2 power 1 over P. You will get exactly the same cone. But do not think that the same is true in higher dimensions as well. So the geometries are a bit different. So let me explain. So this, you would never catch up the original cone for higher dimensions. N is more than or equal 3. Well, for example, let's look at L23. This is our unit. Let's calculate state space. So this is our ball, right? It's a Hilbert space. This is a nice ball. And this is a plane, right? This is a plane. So you are getting this intersection, is it? So suppose epsilon is more than 1. By the way, again, for S1, if you take this S1, you're going to have units ball, and this plane, again, this plane will be tangent to this ball. So intersection, again, nothing, just single point. So, but if epsilon is more than 1, it's okay, it works. But the problem is that you are unable to catch up this triangle. This triangle is sort of state space of the classical cone. But all our states, they have a rounded shapes. No. Yes. So you would never catch up the same code in this case. So this operator positivity, it has the rounded state space. So, but this one is not, right? So this is a bit different. So that's a point. That's why they are different codes. Okay, next example. Let's analyze the case of the LP spaces here. Suppose tau is a locally compact, sigma compact, Hausdorff topological space, equipped with a finite radon measure. Again, we can normalize over unit, right, like that. So the all unital star normal space. For p equals infinity, again, we have a von Neumann algebra, and everything fine is there. It's an operator system, ball is unital, no problem here. But for p less than infinity, we have a problem. That's not the case for p less than infinity. Again, we have to enlarge our state space like that, right? So again, if you wish to plug in here epsilon equals 1, the original 1, you will get again nothing, just single point. So ball is not unital again. So here you have to use geometry of balls of LP spaces using the uniform convexity. You can prove that. Again, the classical S1 state is just single point, nothing here. Yes, but our projective positivity for epsilon, it works. It's nice. It provides a new cone, unital separated cone with the state space, and we have again Cadison representation. Look, this is a nice embedding. I mean, or the isomorphism and isometric sort of using this integration. Look, this is unital, and we have the positivity. Well, this can be generalized to locally convex cases as well, but I do not like to talk about it. So just briefly mention that the same can be done for in the locally convex case too. So there's a nice theory how to develop the ideas in the locally convex case. Now, instead of the single cone, we have a filter base of unital cones. Intersection is separated. Well, if you do something like that, you're going to have, you will end up with this sort of topological space, inductive limit of compact spaces. And you can get the similar embedding here. Anyway, this is another direction, so just briefly mentioning about it. So this one also can be done here. Okay, so original cone of the Banach lattice and our projective cone, well, let's say projective positive epsilon, they're actually totally different cones. Well, unless support is finite. So let me formulate this key result here. So we say that cones are comparable if one of them belongs to the other one for two cones. So because, well, we know they are different, but maybe one of them contains the other one for some epsilon, right? So it seems never. So the cones, they are comparable. They're comparable for some epsilon if and only if support is finite. Look, that's an interesting result. It's telling you even elementary inclusion, it's impossible here. They are quite different structures. One of them sort of operator, the other one sort of lattice structure. Yeah, in the proof we used the nice paper by Norbert. I heard about his talk in our seminar, right? This helped me to understand because there were some stuff from measure theory. The Norbert nicely explained in his paper, and I used it, and thanks for that. This is one of the side effects of our seminar. Like, I saw that I heard about all this stuff, so eventually I got it from this one. Yes. Well, finally, I need a bit more time just to end up this one. The final class is a matrix algebra, is a finite dimensional nice case. What's going to happen for the full matrix algebras? So let's look at Mn. N is more than 1. Well, unit, we have a unit here. We have a Schatten norms, right? Using the trace. So let's use notation sigma p Mn with this norm. For 1 and infinity, we also use Tn and Mn, right? Trace class operators and sister algebra. Well, we know again duality between them, P and Q, right? Using the trace. This is a well-known fact, so we know it. Okay, concerning state space, yes, for Mn plus standard cone, we know the state space consists of all density matrices, right? Y is the positive, trace is 1. This is our state space standard. Well, we can modify it, like with epsilon, more than or equal 1. Epsilon positivity looks like that, right? Sort of, you can estimate the spectrum here, the minimum and maximum, infinite and supreme values of this. Well, here minimum and max of the spectrum of X. So in particular, every positive is invertible automatically. But state space, look, can be described like that. The original lemma, the first lemma concerning the description of the state space, sort of combinations of the density matrices with this sort of range for S. Yes, in the case sigma 2, we know it's a Hilbert-Schmidt matrices, right? So it's a Hilbert space. And every element has a unique orthonormal expansion. Look, this is our E2 again, normalized unit vector. And we can define the sort of cone, like this also cone. One needs to choose the Hermitian Hilbert-Schmidt matrices, which they do satisfy this sort of inequality. So this one automatically should be positive. Well, we met this sort of cone. Let me mention, actually, this number can be reduced to √2. So actually, it's all about this cone. By the way, we met this cone in my paper, Operator Hilbert System. That's exactly the cone that stands behind of the PZS operator space. The PZS operator Hilbert space, actually. It's all about the same cone. Look, that's the main result concerning the comparison result of all these cones. Since it's a finite dimensional case, all of them can be, they are comparable. Look, that's a case. This is the highest one here, standard cone. Then we have decaying down, right, to sigma 1. And look, we can catch up with epsilon more than or equal n. So there's an increasing family of unital cones. And for every cone, we have a precise description of the state space. 2 cone reduced to previous one. Right. Okay. Again, Cadison representation theorem. Look, looks nice like that. So you can realize them like continuous functions using preserving the positivity. Well, for the trace class operators, again, you can get the description of the state space. So one needs to get this hyperplane and intersect with this ball, this sort of cube and this hyperplane, and get this unitary equivalent stuff. That will be exactly your state space. So this is a new positivity, right? Look, using the trace like that. And is running between Mn epsilon plus Mn for epsilon more than or equal n. So here we can get this nice precise description of the state space using the finite dimensional geometry, what's happening here, right? Yeah, but concerning positivity again, so could we get, again, original positivity? We know they are comparable, but again, the result very similar. Like in the LP case, this equality, state of the trace class positivity and standard density matrices, they are equal only if n equals 2. Yeah, that's a so-called in qubit case. We have the original positivity on the qubit case. But even for n equals 3, look what may happen. You can get these diagonal matrices. They're going to be some points of the state out of this density matrices. For example, if you get this matrix, diagonal 2, 0, 1, this is a positive matrix, but that won't be positive in our sense. It's not projective positive. Because if you calculate trace x with, for example, with this one, it's going to be negative. So this is something strict. So projective positivity should be something strictly positive eigenvalues here. Well, finally, I skipped this part. Whatever I said concerning Mn can be generalized to a finite von Neumann algebra case with the faithful finite normal trace. And again, interesting moment, like if you look at the L2 case, it's again reduced to, it defines the Pizier's operator Hilbert space structure. The same cone that stands behind of this Pizier's Hilbert space, right? Look, concerning epsilon, you have to choose this sort of epsilon. That will be enough, right? Okay, yeah, let me stop here. Okay, thanks for your attention.
Okay, thank you very much. Yes, and what about questions or comments? Oh.
Thank you very much for an interesting talk. So
Thanks.
could you maybe go back to your example involving functions whose natural logarithm had bounded variation?
Yes, sure. Let's go back.
Okay.
It was somewhere here, right?
Yeah. This
okay,
is
yes.
This is the one.
Yeah. Epsilon oscillation. Either 0 or we have this sort of estimation for ln of this function. Yes.
Is it obvious that this cone is closed under linear operations?
Yes. Closeness of the cone is not a big deal, as I guess. So, should I? Yeah. Well, anyway, there are plenty of ways how to do it, but it's not so hard to prove it. The problem is that you need to clarify what's the meaning of this inequality. If you get some exponents, eventually you will end up with something like that. Let me show you here. Look, something like that happens. It's all about this one. Yeah, they're totally equivalent for this epsilon. So that's why the closeness comes out from here.
Oh, I see. So
yeah.
It's kind of duality. Duality takes care of
everything.
Yes,
that's true. Yes. So the dualities, you can generate all this stuff. You can get this. There's going to be a closed unital nice cone. Yes.
Okay. Thank you very much.
Okay. Yes. Thanks. Pleasure.
Okay.
Yes, please. More
Other
questions?
Other questions? Yeah. No. So if not, let us again thank for excellent representation and very interesting things which you succeeded to prove. And so today we part, and next week, let me emphasize, 5:30. We shall hear Timur Oilberg. Yes. So, bye.
Thank you.